In this video, we'll be discussing an example of the process of conducting a confirmatory factor analysis. For this example, we're going to be looking at the output from three different competing models regarding six survey items. The first one will have all six items loading on a single factor. The second one will have two factors, which each have three items where the factors are completely unrelated or are orthogonal. And the third model will have two factors with three items loading on each factor where the factors are allowed to be correlated, that is, they're oblique. We typically in structural equation modeling don't run the second one. So the second one with orthogonal factors is not very common at all to see. Typically, you'll see the third model just straight away, which is, I believe, the items load under this particular factor, and you'll just see that done. Not, again, two factors and three items each necessarily, but I believe these particular items load under these particular factors, and you'll just see it that way. Sometimes you will see kind of a unitary construct. Does it work better to just have a single factor underneath for purposes of comparison? But that is not necessarily given, and it's not necessary to do this. We're doing this more for practice in terms of comparison. So we'll assess the model fit for each and then compare the models and the item fits and discuss next steps. So first of all, let's look at the models that we want to fit. So this first one, I have all of the items loading on a single factor as we described in the bullet point. For the second one, I have two factors, each of which have three items loading onto it. But you'll see that for these two factors, there's no relationship between them. That is, there's nothing connecting the factors to each other. This third model, I have the exact same setup as the second model, but now I have a line connecting factor 1 and factor 2. So this is indicating that I have the three items under factor 1, the three items under factor 2, same as second, but now the underlying factors are allowed to have a relationship. This third model can be related to the first model in that the third model, if the correlation between factor 1 and factor 2 is 1, that arrow connecting the two is 1, then that would indicate that these are the same and that they're a unitary construct, which is what's represented in the first model. Similarly, the third model is related to the second model in that if the relationship between factor 1 and factor 2 is set to be 0, then that would be the second model. So we can see a bit of the nesting structure, though again, that's not the point. All right. So after fitting the models, we can go ahead and look at the fit statistics for each of these, assuming I've checked all the assumptions behind the scenes, etc. So I'm going to look in this analysis at the chi-squared and degrees of freedom. Normally that's reported with a p-value, but I'm going to skip that for this case. The IFI, the TFI, or the TLI, excuse me, the CFI, the RMSEA with a 90% confidence interval. And for the purposes of what we're going to do in this class, I'm not going to worry about the confidence interval. I'm just going to look at the RMSEA number itself. The SRMR and the AIC, which again can't be interpreted without comparable models. So looking at the first model, that is all of the items load on a single construct, I can see the chi-squared and degrees of freedom. I don't show the p-value here, but the p-value is very, very small, indicating that we are statistically significantly different from perfect. And yep, we sure are. The IFI shows bad fit. The TLI shows pretty bad fit. The CFI shows, bad fit. RMSEA shows bad fit. SRMR shows bad fit. And AIC we can't interpret. So model 1 objectively looks pretty bad. All right, looking at model 2. So I look at the chi-squared. The chi-squared looks better. Because these models are not nested, I can't do a chi-squared test between them. The IFI looks acceptable. TLI looks low, arguably marginal, but no, probably too low. CFI looks acceptable. RMSEA really is probably too high to be acceptable, probably pretty bad. But is better. The SRMR got worse, um, pretty noticeably worse. And I don't normally compare the fit indices across models, save for the AIC, but it is interesting to note that, particularly because, again, remember the unique thing about SRMR. SRMR is tied into the underlying latent factor structure. So the change from a single unifying factor to two distinct factors, this seems to be picking up that change was a bad thing, so that maybe these factors should potentially have a relationship between them. Epic foreshadowing there. Um, the AIC in Model 2 is better than Model 1, and that's the comparison we make. We look at the AIC in Model 1, AIC in Model 2. AIC in Model 2 is less than the AIC in Model 1, so we say Model 2 fits better than Model 1. But notice that by saying Model 2 fits better than Model 1 according to AIC, that doesn't mean Model 2 fits good. In fact, this Model 2, I would say, probably doesn't look like it fits well. It might be borderline in a couple. CFI, IFI look okay. TLI looks low, but somebody could argue borderline. I'd probably disagree, but whatever. In any case, the model fit is either very borderline or bad. I'd argue bad, but the AIC indicates that Model 2 is better than Model 1. So relative fit and objective fit are different things, or overall fit are different things in that, again, a model can be relatively better, but still objectively bad. All right, so looking at Model 3 is actually nested within, well, we kind of discussed Model 1 and Model 2. We won't go into the details, but I can tell you Model 3 is statistically significantly better than Model 1 or Model 2. So that's good to know in terms of comparative fit. Real quick, I'll skip the fit indices and go down to AIC, talking about comparative fit. AIC, the bottom statistic, is better in Model 3 than in Model 1 or Model 2. So, according to both the chi-squared significance test and AIC, Model 3 is looking better, which is good to know. Now, again, is Model 3 good? Well, we don't know that yet. Let's go explore. But Model 3, even if it's not good, is better than Model 1 and 2 at the very least. So, let's see if it's good. Looking at IFI, yeah. Oh, man, IFI looks great. TLI looks good. CFI looks great. RMSEA, that's borderline. That's borderline. SRMR looks great. So taking all of this together, again, SRMR and then the 4 IFI, TLI, CFI, RMSAA, those, taking all these together, I think this looks pretty good. Looks like a good overall model fit for Model 3. And again, relative fit, and it's relatively better than Models 1 or Model 2. So I will note, I don't show it here. The chi-square typically has a p-value associated with it. RMSEA doesn't always have a p-value associated with it. Typically, it has these confidence intervals, and I did report those here. And of course, Model 3 looks best. Right. So I'm gonna show the graphic of Model 3 with the loadings put on the graphic. As a side note, often these loadings are provided in table form, not on the graphic form. It's one of the nice things about Amos is that it can show our statistics on the graphic, not the fit statistics, but in terms of the item loadings and stuff like that. So this is kind of nice. I can see that factor 1 and factor 2 are indeed correlated. Moderate correlation is what we typically call that. I can look at the factor loadings of visual perception, cubes, and the flags test, as well as paragraph composition, sentence composition, and word meaning. For factor 2, everything looks really good. 0.85 loadings are above all thresholds, all rules of thumb that anybody would have. Factor 1, visual perception looks good, but cubes and flags both look a little low. Kind of depends on if you have who you're using for your cutoffs, I guess. For me, flags is probably fine. Again, my personal cutoff is somewhere with no good reason, somewhere between zero point 0.5 and zero point 0.6. That zero point 0.7 is kind of right on the borderline. That's about 33% of the variance in flags is explained by factor one or is related to factor one. The cubes might be a little bit low, but the other thing that comes into play here is two things. One is all of these paths are statistically significant. So again, we can do a statistical significance test here. So that comes into play a little bit. Cubes is a little low, but it is statistically significantly related to that factor. And the second is that we had good model fit for this model. So I'm less critical of the items when my model is fitting well. I will sometimes go into the items looking for potential changes, especially if the model is fitting poorly, looking for potential places where poor model fit's coming in. Again, any model edits should happen because of theory, but that might be something that I would look at. And again, the low loading a factor one on cubes could indicate that maybe that cubes test is not particularly good. Of course, in this particular case, cubes I believe is the only 3D test. Flags is 2D, 3D. So in this particular case, cubes might represent something unique that's very important for visual acuity, which is the underlying factor of factor one. Now, again, all of these paths can be treated as correlations. So the correlation between visual perception and factor one is 0.78 to some degree. This is kind of handy because you can also look at the variance explained. So the variance explained in visual perception that comes from factor one is 0.78 squared, that R squared value. In this particular case, 0.78 squared is like 61%, give or take. So about 61% of the response in visual perception is due to that underlying factor. And you can calculate that for each one of these particular outcomes. Anything that arrows are pointing to, you can calculate that from. Recall again that 0.7 cutoff is associated with 50% of the variance being explained in the outcome, or excuse me, in the item. So that's why that 0.7 cutoff is there. For everything above 0.7, more than 50% of the item response is associated with the underlying factor. All right, well, now we are on to software. This has been a discussion of an example of running a confirmatory factor analysis and interpreting that with a couple of different options and comparing models and looking at overall fit. So now and item fit. Now we're going to actually practice implementing that in software.